Third lecture on advanced PD, and we are going to talk today about method of characteristic. So this method is one of the most important methods which you can learn and which actually gives you an solution of a PD. I mean, more or less, it can be an explicit solution or an implicit solution, but a solution nonetheless. So let's understand the method with the help of a simple example and linear example actually, and then we'll talk about much difficult, harder problems to solve from there. So first of all, we'll assume the problem in R2, right? So we are going to start with A of xy ux plus B of xy uy equals to 0. So we look at this equation. See, this equation x and y will assume this thing to be from the whole of R2. I mean, you can assume it to be in some omega subset of R2, but I mean, that's okay. For now, we just want to understand what this particular expression means. Yeah. So from the form of this equation, you can see that this one. So let's say this is one. So one is a first order linear PD, right? That much we already know, that one is a first order linear PD. Okay, I want to find a solution of this equation. Yeah. So whenever I say solution, so this is very important. See, we want to talk about the solution of one equation 1. Okay. So first of all, what does that mean? So we have discussed it earlier. Whenever we say solution of one first order equation, what we generally mean most of the time, for this course at least, what we mean is a function, okay, u. Okay. So in C1 of R2 is said to be a solution of 1 if u satisfies 1 for all xy in R2, right? So what we have is, first of all, you have to give the address of the function. The address is C1 of R2. So if you remember, C1 of R2 is the set of all continuously differentiable functions, okay, on R2, right? So that is your C1 of R2, continuously differentiable functions on R2, and I have the solution as some function which satisfies this equation for all xy in R2, right? Now, that's your solution. Now we want to understand what the expression 1 means, right? So, and we want to do that geometrically. So first of all, we will look at the geometric interpretation. Okay, geometric interpretation. Okay, what it means geometrically. See, whenever, let's say, a solution exists. So initially we do not know if there is a solution or not, okay, and what it will look like. For now, just for the sake of understanding, we'll assume that A and B are continuous. A and B are continuous in R2. Okay, so this we will assume, and we also assume that there exists a solution. Okay, see, we do not know if that equation has a solution or not, but initially what we are going to do is we are going to assume that A and B are continuous and there is a solution to this equation. Okay, obviously a priori, I mean without doing anything, we can obviously see that u equals to 0 is always a solution of this equation, right? This is a homogeneous equation, so u equals to 0 are always solution. Okay, so this is a small note before doing anything. Let's just look at this thing. U, the trivial solution, is always a solution, always a solution of the homogeneous equation, right? Homogeneous equation 1. Okay, but I mean we are not interested, but we will only be interested in non-trivial solutions, because trivial solutions are not very important, right? So let's look at the geometric interpretation. So we rewrite this equation, rewrite 1 as follows. So I will write it like this: a, okay, of x comma y, b of x comma y, and 0 dot ux of x comma y, uy of x comma y, and minus 1. This is equals to 0. Okay, so can I do that? Obviously I can. This is just a dot product for a fixed xy, so you take any xy in R2, and if I write it, I can obviously rewrite 1 like this, because that will give me a of xy ux plus b of xy uy equals to 0, right? Now what is the significance of this, and what makes it so special? See, what happens is this. First of all, let us define some notations. Define S to be the graph of u. Okay. Now, since u is C1, it is given. We are assuming there exists a solution. Solution u, let's say solution u. So, if there is a solution u, the graph of u is smooth. Okay. Define S, which is the graph of it, and since u is a solution, S will be a regular surface, right? Regular surface. Okay. So what I meant by this is, for every smooth surface, not a regular surface. Let's put it like this. It is a smooth surface. And what I mean by smooth surface? By smooth surface means smooth surface. What does it mean? It means that there exists tangent plane, okay, to S at every point. So every point admits a tangent plane, right? So that's your smooth surface. Of course, whenever I am saying smooth surface, I am assuming that it is in R3. So of course, this is another small note. You guys already know this, but let's just put it like this: graph of u. So that is your S. This is defined like this, no? It is a set of all those xy, u of xy, such that xy is in, for now it is an R2. If you are assuming xy from omega, then this is from in omega, but now I am just assuming it is in R2, so it is in R2. So that's the graph of u. Of course, this is contained in R3, okay, and this is a surface in R3, right? So it will look something like this. Let's say that's your axis, and it will look something like this. Okay, it will look something like this, right? So for any point xy, so let's say this is your axis xy, okay, for any point x and y, this point is called xy, let's say. So the graph of the point corresponding to the xy in the graph of S, so this is your S, the surface S. So this point will be x comma y comma u of x comma y, right? So that's your graph of u. Now this is a regular curve, so at every point you have a tangent vector, right? So tangent plane, let's say this point has a tangent plane, okay, and you also have a normal to that plane, right? So normal at the point xy, that will be given by u of x comma y, u of y, x comma y, and minus 1, right? That's your normal at that point. At this point there is a tangent plane, and the normal will be given by ux at the point xy, uy at the point xy, and minus 1. This we already know from basic calculus courses, right? Okay, now once we have this normal, see what it means is, let's look at this equation. See, one can be written like this, no? And at any point on the surface S, if this is the normal, it means that A, B, C dot this vector, the normal vector is 0. It means A, B, C, A, B and 0, this vector, yeah, this always lies on the tangent plane, right? So this implies, let's say that is your 2. So from 2 we have A, B, 0 lies on the tangent plane, okay, of S at xy, right? At that point xy, there is a tangent, sorry, this is xy, u of xy, okay. So at the point xy, u of xy, there is a tangent plane, and it means that a, b, 0, this vector, this lies on the tangent plane, because the dot product of this vector with that normal, okay, is 0. Right. So we have this idea that and this holds for any point xy. Xy is an arbitrary point in R2, right? This holds for any point in xy. Right. So since A, B and 0 lies on the tangent plane of S at the point x and y, u of xy, hence what we can do is we can use this information to actually find what S is. See, S is the graph of u, right? And u is the unknown. So if we can somehow, get to know what S is, we can extract what u is from there. Right. Now, we need to construct. So construction of S, right? That's our goal now. How to construct S. Now you see, let's say that is the surface, yeah, this is the surface which we need to construct. This is your S. Now this point is your point xy, u of xy, okay. Now let's say this is any curve on the surface S, okay, which passes through this point. So this is xy, u of xy, okay, and u of xy, you can understand that's the z coordinate, right? Yes, u of xy is a z coordinate. So let's say this is C of S, some curve. Let C of S, which is given by x of S, y of S, z by S, be a parametrized curve, yeah, on the surface S, right? So C of S is a parameterized curve on the surface S, and obviously it passes through the point x, y, u of xy. Clear? So essentially what I am trying to do is this. First of all, I want to construct the surface S, right? And for that, first we start with finding a curve C of S, parameterized with the help of S. Okay? So S, you can assume, this is small assumption, S is in some interval I, right? Now we want to find what C of S is, right? Now we know something about C of S, and that is this. See, C of S lies on the surface S. S is a smooth surface. So C of S, I can talk about the tangent vector, tangent to this curve, right? So tangent to C of S, so that is given by C prime of S is given by X prime of S, Y prime of S, and Z prime of S, right? C of S, C prime of S, which is given by T prime of S, Y prime of S, and Z prime of S. This is a tangent at this point, no? So this is a tangent vector at this point, okay? At this point. And this tangent vector should lie on the tangent plane, correct? So this tangent vector should lie on the tangent plane. So the tangent plane at this point, let's say this is your tangent plane at that point. So this vector should lie, C prime S should lie on the tangent plane, okay, of S at the point x, y, u of x, y, right? This should lie. Now, you see, the choice of C of S, right? The choice of the curve is on us. I mean, we can choose whatever curve we want. Huh? As long as the curve lies on the surface, right? Lies on the surface. See, we want our curve, and we know that there is a vector. Which vector? This vector, A, B, 0, that lies on the tangent plane to S, right? This vector lies on the tangent plane. So, we'll assume that our curve, so we are basically looking for a curve, parameterized curve C of S, which looks like this, such that the C prime of S should look like this, okay, this vector. So this vector also lies in the tangent plane, and this is another vector which we have constructed, x prime, y prime, z prime, which lies also on the tangent plane. Yeah, we want this curve C of S to be such that x prime S equals to A of xs, ys, y prime S equals to B of xs, ys, and z prime S is in this case 0. Okay, we want this thing to happen. Okay, so should lie on this thing, and such that, okay, so please understand here, it's not that any curve will do this thing. We want a curve, we want a parameterized curve which lies on S such that at any point on this xy, u of xy, at that point these three equation holds. Okay, see, A, B, 0 lies on the tangent plane, and this thing, this curve is on our hands. We want the tangent vector to this point, at that point, to represent this particular vector, right? So this, we get three such equations. See, these equations are called, so let's say this is your q, okay. Now q has a very special name. So q, so the equation q, this is a system of equation, three equations. Q is a system of equation, okay, system of ODEs. As you can see, it is ODEs, yes, system of ODEs, and are called the characteristic equation, okay, of the PDE1. Clear? So given the PDE1, the system of ODE is Q, which looks like this: x prime S is A, y prime S is B, and z prime S is 0 in our case. Okay, that is called the characteristic equation. Of course, if you just I mean, you can change 0 to C of xy. So basically, if you have an inhomogeneous equation, then you can just take that C here. It's not a problem. But anyway, let's just do it this way. Okay, now if we have something like this, see, this is a system of ODEs, right? And we know that if A and B are given to be continuous, there is a solution to this equation, right? So by Picard's theorem, so this is the theorem on ODE, the existence theorem, Picard's theorem. We have the existence of a solution. Okay, now this solution can be a local solution. Okay, we do not know if it is a global or not, but we know that there is a local solution at the point, whatever point we are looking at, that point x y u of x y, around that point this is a local solution. Okay, so let's say the solution which we get, it will be xs ys zs, right? So you solve this equation and you get xs ys zs. This is the solution you get. Okay, so this lies on s, right? And this actually is the curve c of s, right? So c of s, this c of s is called the existence of solution, this which is given by this. Okay, right? Now this curve c of s is called the characteristic curve or the integral curve for the PD1. Okay, so c of s, so c of s is called the integral curve to the PD1, right? Now take the union of all such curves. Okay, once you do that, then that should give you your required surface, and that surface will be called the integral surface. Okay, so union of so take the union of all such curves which should give s. Okay, s is the graph of u, and we call s as the integral surface. I mean, this is not a very standard practice to call it, but we will just call it an integral surface to the PD1. Okay, but C of S is always called an integral curve. So essentially what is happening is a curve on the surface S, that is always called, we solve this particular equations, is called the integral curve. These particular three equations are called integral equation, characteristic equations, and the surface which you get by taking the union of all such curves is called a integral surface. Okay, now let us take up an example and see how all of this works. So example, let's say you have this equation ux plus uy, ux plus right, let's say this is aux plus uy equals to 0. Let us take this. See, I am starting out with a constant here. So a is a real constant and xy is in R2. For now, let's just take that. We want to solve this equation. Of course, u equals to 0 is the solution of this equation. I mean, you don't need to do anything to understand that, right? But we want to find non-trivial solutions. Okay, so what you need to do is, first of all, write down the characteristic equation. So let's say C of S is x of S, y of S, and z of S be a curve. So I want this to be an integral curve. Okay, be a curve on S, which is the graph of u. See, this is assuming that u is a solution, which is we already know. Okay, see, u is unknown. We are assuming that there is a solution. I don't know what the explicit solution is. That is what we need to find. I am assuming there is a solution, not an explicit solution. I know there is a solution and I want to find the explicit solution. That is why we are doing all of this. Okay, so let's say C of S is x of S, y of S, z of S be a curve on S for S in I. Okay, so and write down the characteristic equation. So the characteristic equations are given by this. Characteristic equations will be given by this. X prime of S this is the thing which should be corresponding to ux, right? This is given by a, and y prime of s should be something which is corresponding to uy, which is given by 1 here, and z prime of s is here, whatever is on the this hand, this is 0, so this is 0, right? Now let's solve this thing. What does this gives? This gives x of s to be a s plus some constant, let's say c1. The second equation gives you y of s is s plus c2, and the third equation gives you z of s is c3. So essentially what this means is we are z is always a constant, and we are looking for an equation such that x and y will look like this. c1, c2, c3 are arbitrary constants. Okay, so here these are the integral curves. Okay, these are the integral curves for c1, c2, c3 in R. Okay, arbitrary c1, c2, c3. Okay, now you see what happens now is, if we somehow eliminate s from here, yeah, we'll get some relation. So let's do that and see what we get from here. Once we eliminate, so eliminating s, we have x of s equals to a times, so s I eliminated, x is obviously x depends on s. For now we are not going to write this to be depending on x, so we'll just write x equals to a times s, right? And s, see, let's write it, it is a s plus c1, y is s plus c2, and z is some constant c3, right? So what is x? X is y minus c2, y minus c2 plus c1, right? Now if you write it properly, it gives you x minus ay equals to some constant, let's say c4, right? C4 is a constant which obviously depends on a, but I mean a is also a constant, so it does not really matter. Okay, so what we are getting from here, eliminating s, is x minus ay equals to c4. Now what does these three equations say? So it says that so what does this mean? You see, from these two equations we eliminated s and we got this relation. So whenever we are saying there is a characteristic curve, what is the characteristic curve doing? The characteristic curve solves this equation. These are lines, right? It solves this equation, it satisfies this relation along with this relation. So essentially what it is saying is z is constant along these lines, right? These lines x minus ay equals to c4, these lines is in xy plane, right? And z will be constant along this line. So what are the characteristic curves? What are the characteristic curves? What are the integral curves? Integral curves. So integral curves are also called characteristic curves sometimes, but what are the integral curves? It says that, you see, the integral curves, okay, integral curves are given by x minus ay equals to c4 and z equals to c3. Okay, it means that is z. What is z? Z is u of xy, no? Z is the height. Z is the height, which is u of xy. So it says that u of xy is constant along the line x minus ay equals to c4, right? That's what it is saying. See, why z is u of xy, just think about the graph of the function. Let's say that is our graph of the function, right? At any point xy here, let's say xy is any point here, what is u of xy? That's your z, right? That's your z coordinate. So z is u of xy, no? Okay, u of xy. So that is why I am writing it like this. So z equals to u of xy is constant. Z is constant along these lines. Yeah. So you see, let's say x minus ay equals to c4. So those are lines which looks like this on the xy plane. Let's just draw the domain here. Huh? Xy plane, x and y. Yeah. I don't know what a and all of this is. So let's just say that these are x minus ay lines. Huh? X minus ay equals to constants. So these are x minus ay equals to constants. Equals to constant. These are the lines. So what are the integral curves? The integral curves are such curves which are constants, such that u is constant along these lines. Yeah. So if you look at the curve, the graph of the function along these lines, okay, the graph is constant along this line. Huh? And once we get this, we can actually construct a surface out of it. How do we construct a surface? So constructing an integral surface. Integral surface. Let's see how we can construct an integral surface from here. Okay. See, we will define u of xy now. This is a constant, right? So, and x minus ay is c4. We said that u of xy is constant along the line this. So, if you write it like this, let's say this is some function of x minus ay. Yes, if you can write u like this, so you see where x minus ay's are constant, u is constant along those lines, right? This is what it is saying. So these two expression can be written down like this, and this f is in C1 of R. This is very important, huh? Not in R2, C1 of R. X is in R, Y is in R, A is in R. X minus AY is in R. So this is in C1 of R. Why we need C1 we'll explain later. But I mean, these two expressions can be combined together to form this thing. And this is the solution. This is what we claim. Okay. Why this is the solution? First of all, f is C1. If f is C1, u is C1. Okay. So for a solution, u has to be C1. So that implies, therefore, u is in C1, right, of R2. And let's say what is u of x. Let's see what is u of x if you write it like this. U of x is f prime. Yeah. And u of y. What is u of y? U of y is minus a f prime. F prime, why? Because f is just a real valued function. Okay. Now, if that is the case, therefore, let's say what is u of x plus a u of x plus u of y. What happens to this thing? It is a f prime minus a f prime, which is 0. So this holds for all xy in R2, right? So this is 0 for all xy in R2, and hence what we can say is u, which is given by this, is a solution. So clearly f is an arbitrary function, right? Function, and hence one admits infinitely many solutions, right? So, and that is I mean, expected, right? So what we did is, how did we find the surface? We have looked at the surface like this, that the surface S which we are looking for should look like a constant along these lines. Yeah, along x minus ay lines, along these lines, if you look at the graph of the function, that should be constant, and with the help of that we have constructed u like this, f of some function of x minus ay. Okay, so when x minus ay is some constant, it is f of some constant which is again some another constant, and u is that constant, right? Okay, so and f is obviously c1, which actually gives us our solution. So this is how we interpret a linear first order equation. A few remarks here. Remarks. So what we have seen is this. See, a ux plus uy equals to 0. So this is a first order linear equation, right? And what we have seen is any solution u of xy will look like a function of x minus ay, right? X minus ay. That is what we have seen. Now what it says is, it says, so number one, it says that the solutions are constants along the line x minus ay equals to c. So along these lines the solution is constant, that we have already discussed. Number two, this is very important, okay, and this is where the equation gets its name. So this equation, yes, is called a transport equation because it transports information, okay. How we are going to see now. See, what is happening here is this. As I have explained, you have, let's say, let us look at the characteristic lines, okay. So in R2, so this is your x-axis, this is your y-axis, and let's say that those are the characteristic lines here. Let's just draw some characteristic lines. Let us draw these characteristic lines here. Now, why they are called transport equations? See, let's say this is the equation given. So what is the equation? A ux, the equation is a ux plus uy equals to 0, and let us assume that the initial condition, so the data is given on the x-axis. Yeah, so let's say the data is given on the x-axis and it is given by u of let's say x0. Yeah, so the data is given along, see, the function is defined on a whole of xy, right, and the data, let's say this is given only on the x-axis. So u at the point x0 is, let's say, I don't know, maybe g of x. Yeah? For now let's just define g of x to be sine x, right? Now if that is given to you, what can we say? We can actually say that u of x and y, if you put it here, that will give you u of x0 is, therefore u of x0 is f of x, right? F of x, which is given by sine x. That's the initial condition given to us. So that will imply f should be sine, right? F is the sine function, fx is sine x. That's what it is giving. Yeah. So what is happening here is this. See, let's say you are given information u of x0 equals to sine x. Let's say at this point is x naught 0. Okay, and you know what the value of u is at this point. Yeah. Now if you go to this point, let's say any point on the line, on this line, let's say this point is some other point, x1 y1. Yeah, x1 y1, but it lies on this line. What is happening here is this. We know that the solution is constant along these lines, right? So what is happening is, if you know the value of the function at this point, you also know the value of the function at this point, because those are going to be same because they are constants. Yes, and that is why the information which you put on the initial line, so the initial data which you have, that data is getting carried forward using on along these lines, right? So this is why that is why I'm saying this is where the name comes. So the transport equation, the data is transported, right? Transported along the characteristic lines, right? Along the characteristic line. So let me explain again. What I mean by this is, you give a data on here, that data gets propagated along the line, right? So at any point on the line, u is constant, and that is why that data gets propagated along the line, and that remains the same. So that is why it's called a transport equation. transported along the line. Okay, so that's why it's called a transport equation. Now, let us look at it a little more with some initial conditions. So let's look at this equation. So the equation, let's say the transport equation, transport equation. AUX plus UI equals to let's say 0, and U at the point x0 is something, let's say g of x. Yeah, I'm not putting here, I put it g of x to be sin x. Let's assume that g of x is s. Now we have, you can do the exact same thing, and you can say that u of xy should look like g of x minus ay, right? G of x minus ay, right? So is a solution, not a solution, these are solutions. So basically I should write u of xy equals to are solutions. So it's a general solution, you can say it's a general solution. It's a general solution of 2. Okay, but for now, what I'm going to do is this. Now I'm not going to assume that, I mean, of course, you can solve this thing and you can get the solution to be f of x minus ay, and then you put the initial condition and you get that f to be g, and you just replace it, you get the solution. But for now, I am not going to assume this thing. Yeah, we are going to do something else. And this is, please keep this in mind, because this is what we are going to use. So the general method, general method of finding characteristics. Okay, so let's look at this equation. A of xy ux plus b of xy uy equals to c of xy. Okay, and I mean, you want, I can let's just assume it to be a semi-linear equation. C of xy u, it does not matter. Let's just assume this thing, and let's assume that the initial condition is given on this thing, x0 is g of x. Okay, so I am starting out with a semi-linear equation which looks like this: a of xy ux plus b of xy uy equals to c of xy u. C, a, b, c, these are all are continuous functions. This is what I am assuming. These are all continuous functions, and here g is continuously differentiable. Okay, now I want to solve this equation. So let's say, let's write it as p. Yeah, I will use the same sort of idea, the geometric idea behind it, but in a little different way. See, now what we have is this. We have this equation. This is our familiar kind of equation, right? With some, the initial problem was homogeneous equation. This is an inhomogeneous equation. That's not a problem. Okay, but we know how to handle this thing, right? Yeah, using the characteristic equations. Now we are given a additional information that we want our u to do this, that at the point x0 it should look like g of x, right? Okay, so let's write the characteristic equation and see. First of all, I want to do this thing, that we want to find a surface, right? So we should look for a surface S, right? Which is the graph of u. Yeah. And S should contain the curve r0 g of r. Okay, this is r is some interval. So what I meant by this is, see, basically solving this, the first equation means that you are basically looking for a graph of u, right? I mean, you are looking for surfaces which is a graph of u, a regular smooth surfaces. And solve, I mean, if you solve this, you satisfies this data, u at the point x0 is g of x. What it means is the surface must contain and this curve, right? So let's say I am parameterizing the x-axis with r0. So r0 and u at the point r0 should be g of r, right? So essentially what I may mean by this is something like this. See, let's say that is the x y axis, and let us assume that the curve, this is our surface S, this is our S, which is graph of u. Okay, now let's say x0. So any point x0 here, let's say this is x0 0. The surface which you are looking for, that should satisfy u of x0 equals to g of x, right? So I mean, if you look at the corresponding point on the surface, it is x0 0, and u of x0 0 is g of x0 0, right? G of x0. So any surface which satisfies these two conditions has to pass through this point x0 0 g of x0. Okay, and this holds for any point in x axis, right? So I mean, this should contain a curve which is parameterized by r0 0 g of r, right? So this is our new information. So now let's write down the characteristic equation. So so for a fixed s, fix r greater than 0. Yeah, this r is varying on the x-axis. Huh? So let c of rs be the characteristic curve, characteristic curve. Okay, and how should it look like? We will write it like this. It is x of rs, y of rs, and z of rs. Okay, yeah. So see, for a fixed r, so let's say this is a fixed r0, x0 0. So r is x0 here, x0 0. This is the fixed point r0, so x0 0 g of x0. Yeah, this is for r equals to x0. See, we want our characteristic equation, not just any arbitrary characteristic equation. We want our characteristic equation to start from here. Yeah, and after that it should move. I mean, it should start from here and then move outwards on the surface, right? So C of S lies on the surface on S, such that this point x prime of rs, okay, this should be a of x rs, y of rs. Y prime of rs is b of x rs, y of rs, and z prime of rs should be c of x rs, y of rs. Okay, so what I meant by this, what is the prime here? See, here x varies between r and s, right? It is a two variable function. So what does this prime mean? I have fixed r, so this is a fixed r equals to x0, and I'm looking at a curve which emanates from here. It starts from here and goes along on its path which lies on s, right? In such a way that x prime is equals to a, y prime equals to b, z prime equals to c. See, we are doing exactly the same thing, but here just the additional assumption that we are assuming that the curve starts from this line. Is it clear? It's not the line, it starts on the curve. So it starts from the curve and then moves outward, okay, as s increases. So R is parameterizing the data curve. Okay, so this is the data curve. Okay, so we will write, see, gamma of R. So this is the data curve. Okay, data curve, and that is parameterized by R. Okay, this is gamma of R. This is gamma of R. And C of R is, now you fix a R. So let's say here R is x naught. Fix a R on the curve. This is the gamma of R. Okay, this is gamma of R. This curve. You fix a R, and then you look at the curve C of S. This is C of Rs for this fix R equals to x naught. So this is x naught Rs. Huh? Okay, x naught S. We are looking for this such that this derivative is with respect to S. Okay, right. Now this is not the end. We have more information here. So what is x at the point R0? What do you think it happens? See, at the point x naught 0, so R0 is this, so R0, R is at this point, 0 is S equals to 0, right? So when the curve starts from this point, so at that point, what is the first component here? X naught, so x naught is R, so essentially this is R, right? What is the first component of this data curve? R. So at the point R0, S equals to 0. When you are starting at S equals to 0, the first data is R, right? The component. Y at the point R0, what it should be? It should be 0, no? Okay, it is 0. And Z at the point R0, what it should be? See, Z at the point R0, Z at the point x0 0 is G of x0. So it is G of R. Okay. So S equals to 0. It starts from here. S equals to 0. That is why we are taking the initial value R0 G of R. Here. So these three equations. So you are given an equation with the initial data. These three equations are called characteristic equations corresponding to the problem P. And once you solve it, you get the integral. So you see, now, is there a solution for this thing? What is it? This is an ODE, right? It's a system of ODE. So let me put it this way. Let's say this is your Q, right? This is your new Q. So Q is a system of ODE, right? Initial value problem. Its initial values are given, and hence Picard's uniqueness theorem. You can use Picard's uniqueness theorem gives an unique solution x of Rs, y of Rs, and z of Rs in a neighborhood of R0, right? So in a neighborhood of this R0, you get a unique solution. Okay, you get a unique solution. So that solution, let's say x of Rs, y of Rs, z of Rs. This is the curve C of Rs, let's say. This is the integral curve. This is the integral curve. Okay. And simultaneously, the union of those C of S, that will give you a capital S. Okay, that's the surface. So S is in some interval, let's say G. Okay, so once you do that, that is giving you the integral surface. This is integral surface. Okay, so we are doing the exact same thing, but with the initial data here. So once this is clear, let's look at an example and clarify what I meant by all of this. Example: ut plus aux equals to, let's say, 0. Okay, and u at the point x0 is, let us just make it a little difficult here. Let's say this is u, okay, this is u, and let's say u at the point x0 is, let us say it is sine of x. Now, how does this look? See, if you want to write the characteristic equations, okay, so once when you need to solve this equation, you have to write that C of Rs is a characteristic equation where R is parameterized by R is parameterized in the data curve. Okay, so what is the data curve here? First of all, let's see. The data curve is given by R0 sine of R. That's the data curve. Okay, data curve, and C of Rs is the characteristic curve. Okay. So we are writing the characteristic equation. It is given by x price Rs. This is corresponding to x. This is A, right? And t prime Rs. This is corresponding to ut, which is 1, and z prime Rs is corresponding to this thing, whatever is in the right hand side. Here it is u. So this is u is z, right? U is z because u is the height. So z represents the height. So this is z. Okay, what are the initial conditions given to us? So x at the point R0, this is given to be R. Y at the point R0 is given to be 0. And z at the point R0 is given to be sine of R. Right? So this is what is there. Now once you solve it, let's solve, this is, let's say 1, 2, 3. So solving one, x of Rs is As plus phi1 of R, right? And when you put the initial condition and x of R0 is R, that implies x of Rs is As plus R, right? So similarly, T of Rs should be, sorry, this should be T. Okay, I made a small mistake here. This should be T. So T of Rs, T is constant. T is 1 along S. Okay, so T of Rs is S plus phi1 of R. And when you put this initial condition, it will only give you S. So T of Rs is S, okay, and Z prime of Rs is Z. So if you solve this thing, so similarly T of, and if you solve this thing, what should you get? So let's just solve this thing. It is log Z equals to, it is log of mod Z is equals to S plus phi2 of R, right? Now let's put log of sine of R, Z at the point R0, okay? So at the point R0 is, so log of ZRs here, log of ZRs, R0 is sine of, so log of sine R, so this gives you log of mod Z equals to S plus log of mod sine R. Okay, right. Now you can just solve, you can write it properly, and that will give you mod Z, yeah, equals to e power s sine R. Okay, so once you put it together, what we are going to get is something like this. So hence from 1 and 2, see, x is As plus R and t is S. So x equals to At plus R, right? This is what I am getting from these two, and Z is this. So, and now define u of xy to be your Z, which is given by e power s sine of R, right? So this is e power s, e power t, power t sine of r is x minus a t. So that's your solution. So u of a, sorry, this should be t. I keep on writing y, it should be t. So u of xt is e power t sine of xt. Okay. Now let us see that if this thing is a solution or not. So this is what we got. This is our this should be our solution. Yeah. So verify. Ut is e power t sine of x minus at, okay, minus a e power t cosine x minus at. This is what we are getting, and ux equals to e power t cosine x minus at. This is what we are getting, right? So what is our equation? Our equation is ut plus aux. Yeah. So if you multiply this with a and add it up, so ut plus aux, this should give you e to the power t sine of x minus at. Okay, and which is your u, right? So ut plus aux equals to u. You see, this is the equation. So this is the solution. So this is our required solution. Of course, this is C1. There is no need to verify this thing. It's the exponential function. That's a sine function. That's a C1 function. So u of xt, this is the required solution. So with this, we are going to end this lecture.